Okay, so lecture 15, we will continue our discussion on rotational motion, this time talking about rotational kinetic energy. So we've learned before about linear or translational kinetic energy. It's proportional to the speed squared. It's a scalar quantity, so we just need speed instead of velocity. And in the previous lectures, we've been drawing analogies or equivalent quantities between linear motion and rotational motion. And we learned that in rotational motion, the equivalent of mass is moment of inertia. The equivalent of speed is angular speed. Of course, angular velocity is equivalent to linear velocity, but we are only interested in speed when we are talking about kinetic energy. So then in rotational motion, the kinetic energy of a rotating object will therefore be equal to 1/2 times the moment of inertia times the rotational speed squared. If you compare that to the kinetic energy for the linear motion, 1/2 mv squared. So it's then all the concepts we learned, for example, energy conservation and work energy theorem, we can also use them in rotational motion, except that instead of using mass, we'll use moment of inertia. Instead of speed, we'll use angular speed for the energy quantities. And we can also further extend the equivalency of linear to rotational motion into work and power. Okay, so then if we rotate an object through an angle of delta theta, so you have this angular displacement delta theta, then the work done in rotating that object through an angle delta theta will be equal to the torque tau times the angular displacement delta theta. Again, if we compare this to the definition of work in linear motion, work is equal to force times the displacement. Of course, the equivalent of force is torque, as we've learned in the last lecture, and this linear displacement is equivalent to angular displacement, with the angle changing as you rotate the object. And for power, power is still defined as the rate of doing work. Therefore, it's work divided by time. If you calculate the average power, you want the work over a time interval delta t. For rotation, of course, the definition for work will be torque times delta theta. Now, if we make the time interval very, very short, such that we approach a single time, then the power will become the derivative of work with respect to time. Essentially, if we replace the definition of work from here, work is equal to torque times the angular displacement. Therefore, power is equal to torque times d theta over dt. And d theta over dt, this is equal to angular velocity. And so therefore, the instantaneous power at an instant of time or a very, very short time interval is equal to torque times the angular velocity, omega. If we compare that to the linear equation for power that we learned before, power is equal to force times velocity, right? So force, the equivalent of that is torque, velocity is equivalent to angular velocity. Right? So everything we've learned before in linear motion in terms of energy, kinetic energy, potential energy, work, and power, they will all apply to rotational motion, except that we will be using rotational variables: torque, angular displacement, angular velocity, angular speed, right? Okay, so also then the work kinetic energy theorem says work is equal to change in kinetic energy, or final minus initial kinetic energy. This will also hold for rotational motion, but notice how the kinetic energy is now expressed in terms of rotational variables, moment of inertia and angular speed. Okay, so let's look at an example of a rotational motion and applying the concepts of rotational kinetic energy and work and power. Here you have an electric motor. It exerts a constant torque of 10 Newton meters on a grindstone mounted on its shaft. The moment of inertia is given here as a quantity, and the system starts from rest. Okay. We want to find the work done by the motor in 8 seconds, the kinetic energy after 8 seconds, and the average power delivered by the motor. Right, the same problem written here with the first question plus some rotational kinematic equations to guide us, to help us solve this problem. Right, some quantities, the quantities given are summarized here, and we want to find the work done. So work, that's defined as the torque times the angular displacement delta theta. Yeah, this is the definition of work for a rotating object. Okay, so the torque is given 10 Newton meters. Therefore, we need to find what's the angular displacement in this 8 seconds interval. So as the grindstone starts from rest and the motor rotates it, we want to find the angular displacement after 8 seconds of rotation. Okay, so what do we know? We know the initial angular velocity is 0 because the system started from rest, and we know the time 8 seconds. So using the kinematic equations here, what we want to find is delta theta, right? So these 3 equations contain delta theta, but we don't know what's the final angular velocity. Right? So as the grindstone rotates from rest, it will rotate to a final angular velocity omega f, but the problem doesn't say anything about this final angular velocity. So equations, the last 2 equations are therefore not useful for us, and so we use the first equation to find the angular displacement. So omega I t plus 1/2 alpha t squared. Okay, right? The system started from rest. That means omega I is equal to 0. So this whole thing is equal to 0. Right. But then we encounter the next problem where before we can find the angular displacement delta theta, we need to find the angular acceleration alpha. Yeah? So this equation contains angular acceleration alpha. How do we solve the angular acceleration alpha? We learned last time that torque causes objects to rotate, so that if you have angular acceleration, that means that you have a net torque on the system. So the net torque is equal to the moment of inertia times the angular acceleration alpha. Yeah, Newton's second law of motion in rotation, F equals ma translates into torque is equal to I times alpha. So from here, we can solve the alpha. Alpha is equal to the net torque divided by the moment of inertia. Both are given in the information. Torque is 10 Newton meter. The moment of inertia is given to be 2 kilograms meter squared. Therefore, you have an angular acceleration of 5 radians per second squared. Right. Knowing alpha then allows us to go back to the equation for delta theta, and that allows us to solve for delta theta 1/2 times alpha 5, or angular acceleration 5 radians per second squared times time squared, okay, giving us an angular displacement of 160 radians. And finally, since we now know the angular displacement, we can then find the work. So the work done is equal to the torque. This is the equation we're working from. The torque is given 10 Newton meters times the angular displacement 160 radians, gives you 1,600 joules of work. Right, so you can see here that if you still remember the linear equations, then just change the variables into rotational variables. F equals ma becomes net torque equals I alpha, work equals FD becomes work equals torque times delta theta, and of course our rotational kinematic equations. All right. Cool. Right, so next question, find the kinetic energy after 8 seconds. So it's rotating, the object is rotating, therefore we're interested in the rotational kinetic energy, 1/2 times moment of inertia times angular speed squared. Okay. Right, this angular speed, this will be the angular speed after 8 seconds when the grindstone is already rotating, okay, which we actually don't know. We still don't know what this final angular speed is. What we know is the initial angular speed, that's 0. We know the time, 8 seconds. From the previous question, we calculated the angular acceleration, 5 radians per second squared. So we need to find the angular speed here, but we can use our kinematic equations. Okay, looking at our kinematic equations here, right, you want to find omega F. Pretty much, yeah, except for the first one, pretty much these three have omega F. So you can use any of these 3 equations. I'll use the simplest just because there's no reason to make our lives harder. So I'll use the simplest equation to find for the angular speed after 8 seconds. Initial angular speed is of course 0. Therefore, I'll have here 5 radians per second squared times 8. (40 radians per second for the final angular velocity. Yeah, knowing the final angular velocity, we can then calculate for the kinetic energy. 1/2 times the moment of inertia is given 2 kilogram meter squared times 40 angular speed squared. Okay, you also get 1,600 joules. Which, if you recall, 1,600 joules is the same number that you've calculated from A, which is equal to work. So then that also means that the work kinetic energy theorem says that the work done is also equal to the change in kinetic energy, or that's the kinetic energy final minus initial. The initial kinetic energy is of course 0 because you're starting from rest. The initial angular speed is 0. So here we can see that if you wanted to find the kinetic energy, the final kinetic energy, that's just equal to the work done, which you've calculated from before. Right. Okay. All right. So there were two methods of answering this question. Either you use the definition for rotational kinetic energy, or you use the definition for work kinetic energy theorem, where work is equal to the change in kinetic energy. Right. Cool. Is that okay? Yep, and then the final question, average power delivered by the motor. So power, it's defined as work over time. Maybe you've calculated the work, 1,600 joules. This work is done over a time interval of 8 seconds. Therefore, the power is 800 watts. Oh no, 1,000, of course, 1,600 divided by 8 is not 8. That's 200 watts. All right, any questions so far about rotational kinetic energy? I think up to this point, we're okay, we can follow, which is good. Now let's talk about a special kind of rotational motion. This special kind of rotational motion is called rolling. So in rolling, when an object rolls, I think I have here, yeah, when an object rolls like this, we can see that aside from the object having rotational motion, yeah, aside from the object having rotational motion, as the object rolls, it also covers like a translational distance, right? So rolling is a combination of rotation, and as the object rotates, it has some translational displacement. So this is a what do you call this? A time-lapse picture of rolling. The yellow line here shows a straight line, and this is the motion of the center of mass of the object. So yeah, you have a circular object here. The center of mass is at the geometric center. So right here, as the object rolls, this yellow line, this yellow streak traces the path of the center of mass. We can see that it's just a straight line, meaning the center of mass has undergone translational motion. It's just like linear motion, while the rim of the object as it rolls traces out this red curve here. So the red curve, which is called a cycloid, gives us the information about the rotation of the object as it rolls along. Right, so when the object rolls, say for example, this object rolling from this position to this position, covering this arc length S, subtended by this angle theta, right? So we're just looking at the rolling motion through this arc length S, which is covering an angular displacement of theta. The the linear or translational displacement of this arc length will be equal to the radius times the angle theta, right? So if we measure, if you have a wheel, for example, and you're looking at the rolling of the wheel from this point to that point as it rolls across those 2 points, and you get these arc lengths and stretch it out, the length of that arc length through which your object rolled will be this, this length here, right? Okay, so this arc length S, if you stretch that out, it will give you how far along your object rolled along the linear path. So this arc length will be equal to this translational displacement, and that's equal to the radius times the angle theta. Yeah. Okay, if I get the derivative with respect to time of both sides here, so I have ds over dt is equal to, the radius is just constant. The radius of the rolling sphere is constant, so that's just r times the derivative of d theta over dt. By taking the derivative of the displacement with respect to time, I'm essentially looking at the change in position with respect to time. Change in position with respect to time is equal to the velocity, and the change in angular displacement, angular displacement with respect to time is equal to angular velocity. Okay. So therefore, we can relate the linear motion of the center of mass to the rotational motion of the object. So this one V, this is linear velocity. It's equal to the radius times the angular velocity. So omega, remember, it's angular. If I also take the derivative of this velocity with respect to time, so if I get d vcm over dt, radius is again constant, so I'm just getting the derivative of angular velocity with respect to time. That's essentially looking at the change of velocity over time. Okay, and we know from definition that change in velocity with respect to time is acceleration. And the right-hand side, we're getting the change in angular velocity over time. Change in angular velocity over time, this is the definition for angular acceleration. So also the linear acceleration of the center of mass is related to the angular acceleration of the object by this equation here. Right. So at any point during the rolling motion, the center of mass will have a translational motion whose linear velocity is equal to the radius times the angular velocity, as we've derived from this previous slide. At the bottom of the wheel or the rolling object, the bottom is in contact with the ground, right? So at the bottom, the wheel is temporarily at rest. So the linear velocity is equal to 0. This picture here shows us some illustration where, at the top of the wheel, it's quite blurry. And we know that if you take fast moving objects, that will result to blurry pictures. So this shows us that at the top of the motion, the wheel is moving faster compared to the center of mass, and at the bottom, it's almost the wheel is stationary. So the linear velocity at the bottom is 0. So the reason for this is because you have static friction between the wheel and the ground, and the static friction is the friction related to rest or stationary motion. So you have linear velocity equal to 0 at the bottom, and at the top, the wheel will be moving faster. How fast? It will be twice the speed of the center of mass. Why is it twice as fast? Let's look at the combination of the translation and rotational motion. So we said that rolling is a combination of translation and rotation. So in translational motion, it's as if your object is just moving like this. Yeah, it's not rolling while it's moving. In translational motion, your object just goes from one place to another without rotating. So that at each point along your object, each point will have the same linear velocity, which is equal to the velocity of the center of mass. Yeah. If you look at the purely rotational motion, so your object is just rotating without moving, right? Without rolling, it's just rotating in place. Okay? When your object is just rotating in place, so you'll have, we learned in uniform circular motion that you have tangential velocity at the rim of your rotating object like this. So on top, at the top, you have tangential velocity like so, and tangential velocity at the bottom in the opposite direction. Of course, if you want to look at each point, you'll also have tangential velocity at each point, but we're just interested at the tangential velocities at the bottom and at the top. So if you look at rolling being a combination of translation and rotation, the resulting motion will therefore be 0 at the bottom because you have two velocities in opposite directions. You have the velocity of the center of mass will be equal to the velocity of the translational motion. Okay, during the purely rotational motion, your center of mass is just at the same place, right? It's not moving. And so during the rotational motion, the velocity of the center of mass is just 0. And therefore, during rolling, the center of mass has a velocity equal to the velocity of translational motion. And at the top of the motion, at the top of the rolling object, you have here a linear velocity that is twice that of the center of mass velocity. Okay, rolling will also is also a special kind of motion because we derive this relationship between the linear velocity and the angular velocity. But when you look at the kinetic energy of a rolling object, make sure to include the contribution of translational kinetic energy or linear kinetic energy. So the total kinetic energy of a rolling object will also include the kinetic energy of the linear or translational motion, 1/2 mv squared. So it's just the center of mass that's moving for the linear or translational motion, plus the kinetic energy of the rotational motion, 1/2 the moment of inertia of the center of mass times angular speed squared. For the potential energy, it's still just the same. So regardless of whether your object is moving on a straight line or rolling, it's still the same potential energy because your object is in the same position, meaning h or the height is still the same, and we measure the height from the center of mass. Right, so let's look at this example of rolling and see how this kinetic energy being a contribution of translational and rotational kinetic energy plays out. So you have here the smiley starting from the bottom of the hill, and the smiley rolls up the hill, height h. So there's a correction here. We should measure the height h from the center of mass of the smiley, because assuming that the smiley has some height. So let's just measure the h from the center of mass here. At the top of the hill, the smiley stops, so its final velocity is final speed is 0. What should be the smiley's initial velocity, or in magnitude wise initial speed, for it to be able to roll up the hill with a height h? The moment of inertia of the smiley is given to be 2/5 mr squared, meaning it's a perfect sphere. The moment of inertia of a sphere is 2/5 mr squared. Right, so everything we learned before in terms of conservation of energy still applies to rolling motion and rotational motion. So that means that as the smiley rolls up the hill, whatever kinetic energy the smiley had initially will be transformed into potential energy at the top of the hill, especially since the smiley will stop at the top of the hill. Right, so that's the answer there, but let's look at how we get that answer. So same question, just written here, but we know that energy is conserved. So the kinetic energy at the bottom should be transformed to the potential energy at the top. The smiley rolls. So when you work out the kinetic energy, your kinetic energy should be a combination of the rotational kinetic energy, moment of inertia of the center of mass, times angular speed squared plus mv plus the linear kinetic energy of the translational motion. So that should be equal to mg, height of the center of mass. Okay, so how do we solve this? We want to find the initial velocity VCM. So this will be the initial velocity VCM at the bottom of the hill. So we cannot just rearrange this as so. So VCM already appears here, but remember that the angular velocity, angular speed is also related to translational speed, right? So we learned in the previous slides that the translational speed is related to the angular speed via the radius times the angular speed. So therefore, your angular speed should be linear speed divided by r. And of course, we know that the moment of inertia of the center of mass is given 2/5 mr squared. Okay, so using these two information, we'll substitute that to the equation for the rotational kinetic energy. Will become 1/2 times 2/5 mr squared. Okay. Angular speed expressed in terms of the linear speed will be v over r squared. Okay, plus you have the translational speed component, 1/2 mv squared is equal to mgh. Yeah, don't know what's going on. Some ghosting going on, but all right. Okay, so you have now this expanded equation here. The mass will cancel out, of course, it appears everywhere. The radius will cancel out for this case. What else? 2 here will cancel out. Then we can rearrange everything. Or you have 1/5 v squared plus 1/2 v squared is equal to gh. Okay. So this will be 10 over 7, 7 over 10 v squared. is equal to GH. So therefore, V is equal to square root of 10/7. Good. Right, did we follow the solution here? Okay, yeah. So it's still conservation of energy. There's just this added complication of, adding the rotational motion. And then remember that rotational or angular speed needs to be expressed in terms of angular velocity. So you only express this, you only use this relationship, angular speed is equal to linear velocity over r, if the problem is involves rolling motion. If it's just purely rotational motion, then you don't have to worry about omega is equal to v over r. Just simply use 1/2 I omega squared is equal to mgh, as we've seen in the earlier example. Okay, so then where kinetic energy theorem also holds for rolling motion, total work also is equal to change in kinetic energy. But notice also how you need to include the linear or translational kinetic energy corresponding to translational motion plus rotational kinetic energy in your calculation, both after or final and initial, in the final and initial conditions. Okay, so when you also rolling down an incline, okay, even if there is friction, so the key idea I just wanted to point out in this slide is that even though friction is involved, so when we were looking at just purely translational motion, when there was friction, we said that friction dissipates energy, and so you have to subtract the work done by friction. In rolling is quite different, because in rolling, even if there is friction, the kinetic energy, the mechanical energy is conserved, so that the total potential plus kinetic energy before and after would be equal. It's as if friction doesn't dissipate energy in rolling motion. Yeah. In other words, I think that is the key idea I wanted to emphasize here. Friction doesn't dissipate energy during rolling. What is the role of friction during rolling? Friction provides the net torque that will cause the object to roll. Without friction, what will happen is that the object will just slip down the incline, but friction provides the necessary torque to cause the object to roll down the slope. And so even if friction is there, the mechanical energy is conserved. You don't have to worry about subtracting the energy dissipated by friction, right? Okay, so this example here shows us a sphere that rolls down an incline. Again, I'll correct the height here. Let's measure the height from the center of mass. Okay. And the moment of inertia of the sphere is given to be the diameter times the mass r squared. The diameter will change depending on whether this is a sphere, or if you translate it, it becomes a cylinder, then this d will change. So we're just looking at a general object here whose moment of inertia is d times mass times r squared. Yeah. It rolls down the incline. Okay, it rolls. So it rolls, it does not slip. That means there's friction in the incline that causes the object to roll. We want to find what will be the object's linear speed at the bottom of the incline if it started from rest. Okay, so let's look at this example. So it started from rest. That means Initially, the linear speed and the angular speed is equal to 0 at the top of the height h, and then it rolls down here. So again, the conservation of mechanical energy applies here, even if there is friction in the incline. Right, so that the potential energy at the top will be converted to kinetic energy at the bottom. Yeah. The potential energy, regardless of whether translation or rolling or rotation, that will always be mgh. Okay, height of the center of mass. Okay. That will be the total energy at the top is purely potential because your object is at rest. Potential energy is mgh. At the bottom, the object is rolling. So your kinetic energy should also include 1/2 mvcm squared, include the translational kinetic energy plus rotational m omega plus rotational, oh sorry, not m, it's I. Rotational kinetic energy here. Moment of inertia I omega squared. Right, as I've said previously, if it's rolling motion, then we'll always have to express the angular speed in terms of the linear speed, because during rolling, angular speed is related to linear speed. So then we also have to write this down as mvcm squared plus 1/2. So I'll substitute I with the given moment of inertia. This is dmr squared. And the angular speed should be expressed in terms of the linear speed, v over r squared. Right. Okay, so we can simplify this. So this r squared will cancel with this. The mass will cancel from both sides of the equation. What else? Okay, so then GH, I'll just remove the subscript center of mass because we're clear that we're looking at the motion of the center of mass anyway. So GH is equal to 1/2 v squared plus 1/2 v squared d. So we still have the d there, 1/2 d v squared. Okay. Right. And therefore we can rearrange this. The speed at the bottom of the incline will be 2gh divided by 1 plus d square root. Right. Okay. So you win some, you lose some. You don't have to worry about friction in the sense that you don't have to worry about energy dissipated, but you have to then worry about translational kinetic energy plus rotational kinetic energy during rolling motion. Okay. All right, conservation of energy is still conserved in each case.